All right, everybody. Well, now we're going to go ahead and take a look here at section 4.6.2. This is going to be extending again, or related to, the ideas that we talked about in the last section. So as I state right here at the top of the notes, like in cylindrical coordinates, these new idea that we're talking in this section, which is spherical coordinates, is just a coordinate system that's designed to help us evaluate certain kinds of integrals in a slightly easier way. So again, all we're really doing here is introducing new ways of kind of navigating around 3 space to arrive at particular points, like this black point in the picture. Again, with x, y, and z coordinates, we can traverse down the xy axis and up the z direction to arrive at a point. In the last section, we saw we could kind of use polar coordinates to move around the xy plane and then move up or down with z. But here, we're going to kind of use completely different sets of coordinates, but kind of similar to some of the stuff we had done before. You'll notice here that in this picture, what we actually have are 2 different angles that we're going to use. We're going to have a theta and a phi, and then we're going to have this value of a rho that stands for a distance that we move out to a point. So you can almost kind of imagine this idea of spherical coordinates as kind of like an aiming and a shooting sort of a game in 3 space. These 2 angles are going to kind of tell me how far left to right I kind of need to rotate. Like you could imagine if you held your arm out right now and rotated left to right, you would be changing the angle of theta. But if you were to then rotate your arm up and down, you would be changing the value for that angle of phi. And then rho would indicate how far out you were going to shoot an object out into space. So these, if I knew these values, I could also navigate to pretty much any point out in space that I wanted. If you could just tell me how far to rotate in the theta direction, how far to rotate in the phi direction, and how far of a distance to move in rho. Okay. So from this picture, we can go ahead and deduce a lot of interesting things right off the bat. First off, I'm going to go ahead and add a couple different pieces of information to this picture. You'll see that we still kind of have our regular old x, y, and r that I would have had from normal polar coordinates sitting down in that xy plane. And I can also then see that there is some interesting cylindrical coordinate connections because I could label kind of this vertical side right here as a coordinate of z, right? That's how high I have to go to that point. But of course, from this, I'm going to go ahead and be able to kind of focus in on this particular triangle that will get formed right here. I'm going to think about some of the things I can state about that triangle. One of the things I'll notice right away is that that triangle is kind of part of this larger rectangle that I'm outlining here. And so that'll become very, very convenient for us to take a look at and try to work with. So from this picture, I think we could go ahead and try to sketch out that red triangle. And here's how I'm going to draw it out. I think it looks something like this. That perfectly vertical side there is the side that's associated with z. So if I was to label this side, this is side z. I know that the top side of this corresponds as the same length as the bottom side, which we called r. But of course, we also know that r is the square root of x squared plus y squared. And we know that from polar coordinates. So if I wanted to find this slant side, which represents rho, that's not too hard. I just use Pythagorean theorem again, but on the red triangle. So I would say z squared plus r squared is equal to rho squared. Well, that would mean that if I had r squared plus z squared equals rho squared, and then I square rooted, I could find a formula for the value of rho. Now, in addition to this, I can see that in this picture, the angle phi is located right here. And so I immediately get some other observations. So I'll say here that we notice that z itself is equal to rho times the cosine of phi, and r is equal to rho times the sine of phi. You could check that some right triangle trig ratios. We also know, though, from previously, as in from previous sections, we know that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. And so if I kind of put all this information together, I can say that from this, we obtain the following. These are some cool formulas that I can start to use. Notice that if r is equivalent to rho sine phi, I could replace this value in for all the r's in the original formulas. And so you can see I still kind of have this r sine theta and r cosine theta, but these values become very nice. What I really think that this is an important thing to remember when I do conversions here, that all of these things are going to have, for x's and y's, they have that r cosine and r sine still sort of shape. They've just been kind of updated with what we have here. Okay. We're going to restrict this value of rho to always be considered a positive value. So we're only ever going to think about walking or moving distances out from the origin, not like in any negative direction. And we're going to actually restrict this value of phi to be very special sorts of angles. We're only going to allow it to be angles from 0 to pi. And if you go back to the picture up above, you'll see one other thing that's really crucial about this angle. The way that we're measuring that angle is it's an angle that measures from the vertical z-axis. So if you were imagining, again, using your arm to kind of point out to a spot in space, your default position would be to have your body oriented so you were looking down the x-axis. So you would have somebody that's standing here looking down the x-axis, but then they would start with their arm perfectly vertical and would lower it to an associated height once they had kind of aligned for where the trajectory was that they wanted to move in the direction of. But you have to start from vertical and rotate down. Notice then that if you rotate 0 in that direction, you'll be pointing straight up. And if you're rotating pi, you would go and be pointing all the way down at the ground. But if you wanted to point behind you, you would just kind of move your theta appropriately so you could turn around, and that would allow you to point anywhere out in space. In addition to this, of course, since we have that rho is equal to the square root of the x squared plus y squared plus z squared, it's always possible to square both sides and claim that rho squared is equal to the sum of the squares of those other pieces. Now, really quickly here, I'm going to take a look at example number 1, just to get a sense of how this sort of very weird cylindrical or spherical coordinate system works. So this says here, describe the graph of the following equation in spherical coordinates. Well, this is automatically super weird because I don't even have 2 of the variables involved, right? There's no rho in this formula. There's no theta in this formula. This just says, no matter what, that phi value has to be pi over 6, has to be 30 degrees, if you will. So you could kind of imagine this. Imagine that you stood right now, you put your arm perfectly vertical, so you're pointing straight up in the air, and then you lowered your arm about 30 degrees. So you're maybe still pointing upwards towards the ceiling, somewhere in that range. But then you could have that distance go as far as you want. Imagine your arm could stretch as long as it ever wanted, and you don't care about the value of theta. So you could imagine that you could continue to spin in a circle as you did this. And what you want to think about is, what is the shape that ultimately you would create? Actually try that for a second. See if you can come up with a shape that you might be thinking of. All right, so here's what I got. I said that the graph is the top half of a cone. Specifically, I could imagine it kind of looking something like this. It's a cone that stretches out at an angle of pi over 6, and just continue to try to sketch this out here, right? It doesn't ever stop stretching out. It would keep going up forever, but it's going to look something kind of like this, right? So again, this blue side that I'm drawing here would kind of act as like your arm. And so as you spin around, that's the sort of shape that you're tracing out. So this is the top half of a cone. Okay. All right. In the next examples, we'll take a look at how we can actually use this coordinate system to evaluate different kinds of integrals.